Welcome everyone, good morning. I'm Jasper. I'm a second year PhD student at the Eindhoven University of Technology. And today I'll be talking about my work on hard decision decoding of the OFEC code. So the OFEC code is an extended, is the FEC for 400G pluggables, and is also under consideration for 800G and beyond. It's designed as a code to have very high throughput, while with relatively low decoding complexity. And currently, state of the art aims at to achieve a target bit error rate of 10 to the minus 15 at an input bit error rate of 12.7, as you can see on the figure. The current state of the art implementation using 3 soft and 2 hard hybrid decoding, where it combines Chase-Pindia with iterative bounded distance decoding. The work from reference 2 barely achieves that target. However, this is a very complex, relatively complex decoding algorithm with many BDD attempts. And for that purpose, if you want to lower, especially if you want to go faster, or at lower power consumption, you can consider purely hard decision decoding, just doing bounded distance decoding, where you reduce your complexity very significantly, but at a cost of 1.3 dB in the net coding gain. However, there's an issue with hard decision decoding, which is stall patterns. Stall patterns are patterns of errors that no matter how many iterative bounded distance decoding attempts you do, your decoder will always fail. And this will give you an error floor, as you can see, which means that you no longer have a 1.3 dB difference, but a much larger, where you go 10 to the minus 15, you will be quite a few dBs away, at which point it doesn't make any sense anymore. So there's this initial stall pattern at a bit error rate of 10 to the minus 9, which is still 6 orders of magnitude from your target. And in reference 3, they proposed a very small minimal stall pattern removal algorithm that's quite simple. And this shows that it removes this initial error floor. However, in our work, we already show that there's, even with this stall pattern removal algorithm, a new error floor exists at 10 to the minus 12. Additionally, we propose a new algorithm that removes this, lowers this error floor by an additional order of magnitude. So, yeah. Before I can actually explain the stall pattern removal algorithms, I first need to explain the OFEC code. So, the OFEC code is a block convolutional spatially coupled code, or of the class of general product codes. And it's based, it has the extended BCH code as the component code, similar to the most well-known product codes. So each code word in the OFEC code is a very long semi-infinite sequence of columns with block length n, and where each column is half a code word, or half an extended BCH code word. These columns are then grouped into groups of 2B bits, giving chunks where each of 2B are half code words, and each of these chunks is divided into blocks of 2B by B bits. So, you now have half code words, but for the extended BCH code decoder to actually be able to do something, you need full code words. So, this is obtained through an encoding procedure. Here we're going to encode chunk I is equal to 6. We're going to assume that all chunks before I is equal to 6 have already been encoded and are fully there. So, first thing, we get some fresh information bits marked in blue here, and we're first going to obtain the bottom half of the extended BCH code word, which consists of previously encoded bits. You do this in this staircase pattern, where you load them, apply an interleaver, and put them below. Then we're going to apply extended BCH decoding, which adds the parity bits. Now we can assume chunk I is 6 is encoded. We're going to discard the bottom bits. We don't need those anymore for the encoding. We can transmit the blue and the green part, and we can repeat this process for I is equal to 7. The next step, after you've received your sequence, you're now going to apply the decoding. Decoding is very similar to the encoding procedure with a few key differences. Firstly, you're doing it based on iterations. So rather than just doing it once, you do apply iterative bounded distance decoding or other iterative decoding algorithms. And you use a bunch of iterations that can happen in parallel. So you determine here an iteration marked in purple and marked in orange. Those are 2 separate iterations. They are completely unrelated to each other at any given moment in time. And you can do every step in the decoding process, you can then do them at the same time. So what's going to happen is, again, we're going to now decode chunks IS6 and IS13 in parallel. We're going to, again, load the old information bits, or the previously decoded bits. We're going to apply bounded distance decoding, or whatever decoding algorithm you want. And then, here is the difference, which is key to the iterative part, is you're going to now write back both your updates in the bottom bits and in the top bits. And now we're going to assume the decoding iterations are done, and we're going to shift the window by one, and we're going to repeat this process for IS7 and IS14. So in this case, you can see that the decoders, the shifting, now each bit will be decoded twice per iteration in a repeating fashion, which gives the actual important decoding gain. However, again, for iterative bounded distance decoding, pure hard decision, this suffers from stall patterns. The top left, I'm going to do it based on product codes, because it's just a lot simpler, and it's easier to follow. So, in the product code, each code word is each row and each column is a BCH code word with T is 2, so it can correct each code word, can correct T errors. But as you can see in the figure, there's 3 crosses in all the rows marked in gray, which means that no matter how often and in which order you decode, your decoder will always fail. This will not get removed, the code words will always fail. So, your IBDD will not be able to solve this. However, you can remove these stall patterns by using the results from the bounded distance decoder. So the bounded distance decoder, the component decoder, will tell you one of 3 things. It will tell you either that whatever you put in was already a valid code word, it didn't do anything, it said everything's good. Or it will say, I found errors, I've corrected errors, and will tell you that, which is marked in a 1. Or, in the case of decoding failure, it will return a 2, a flag of 2. And that's what the case for the code word marked here in gray here. And you can use this information to determine if a bit is likely to be a stall pattern or not. So let's first start with the algorithm as a simple case, the algorithm proposed in reference 3. Here what we're going to do, first we're going to do the BDD iterations. Now all errors that aren't part of a stall pattern have been removed. Right? This is just a standard decoding procedure. Then we're going to, each bit is protected by 2 code words, right? By a row and a column. We're going to apply, we're going to assume a stall pattern if both a row and a column, the row and a column associated to a certain bit have failed to decode. We're going to flip all bits where both the row and the column have failed. We're going to assume every bit here is part of a stall pattern, and we're going to flip those bits. So, in the top left, you'll see, we're going to flip every bit where the column, both the row and the column are marked in gray. This is going to remove a lot of errors, add some new ones, but this is no longer a stall pattern. Each row and column has at most 1 error, so we can just do some cleanup bounded distance decoding to clean up all the errors, and we can move on. All right, this is the minimal stall pattern algorithm. It's very simple, but again, this still has an error for 10 to the minus 12. So, for that purpose, I proposed a 3-stage stall pattern removal algorithm. So, it consists of 4 novel algorithms. MRBDD, which is a special version of bounded distance decoding. It's a very small change, but it's very necessary. And then 3 stall pattern removal algorithms, SPR1 and SPR2, are novel. And SPR3 is a variation of the algorithm proposed in reference 3, with some changes added to remove a slightly larger set of stall patterns. So let's first talk about miscorrection reduction BDD. So in larger stall patterns, you'll have miscorrection loops, where a code word will miscorrect, add an extra error. So it will think that it's a different code word from the original code word, add an extra error, and then the competing code word, that's the other big code word protecting the bit, will correct that error, and it will get stuck. It will keep fighting over this bit, telling, no, it should be a 1, it should be a 0. The BDD decoders will then always tell you, yeah, I've updated errors. But some of these failed code words are trailing. They're not actually part of the stall pattern. They're just trying to undo the errors by the stall pattern. SPR1 and SPR2, my novel algorithms, need to know the start of the stall pattern. So what you do, in the decoding step, the last step of the decoding iteration, instead of writing back the bottom red bits, you just don't do that. This will remove all trailing errors, and now the first error that you get marked will be actually part of the stall pattern. It's a very simple change, but it helped. It was necessary and helped a lot. So let's very quickly go over stall pattern algorithms. It takes quite a while to actually go into depth them, but they're still based on flipping bits. But now we're going to assume a flag of 1 or 2, so a decoding success or decoding failure. You're going to, in the first case, you find a stall pattern at a chunk I. You're going to search the associated code words for decoding failure. You're going to flip the bits, similar to the stall pattern from reference 3, and you're going to remove the flags. So the stall pattern removal algorithm doesn't trigger again and undo itself. This removing of the flags is also quite important. Then for SPR2 is very similar. The only big difference is rather than flipping bits in the initial chunk, you flip bits in the next chunk, in the associated chunk. So you look further ahead in time, and you again remove the flags. And then the SPR3, which is just a variation from reference 3, is now you also accept a miscorrection as part of a correction loop, as part of a valid target. That's the only change, but this lowered the error floor significantly because it removed some trailing smaller stall patterns that would get stuck from if you only applied SPR1 and SPR2. All right, so let's go over the results again. So previous work showed that you could achieve stall pattern-free decoding down to 10 to the minus 10. However, there exists a second stall pattern with an estimated gap of 1.8 dB compared to the 1.3 dB, the previous one. We proposed a new algorithm which showed a 0.2 dB gain. We lowered the error floor by an order of magnitude. And we achieved these very low bit error rates, 10 to the minus 14, using GPU simulations. So I had to, at the end, simulate for over a week on multiple GPUs just to get this low with handwritten CUDA code. While still a 1.6 to even a 1.3 dB gap is quite large. Well, firstly, we can lower the error floor, and additionally, these algorithms with these error floor can also be extended to some soft-aided algorithms or some miscorrection-free algorithms, which have a lot smaller gap, but still the much lower complexity. Right. Thank you very much. My name is Jasper. I'm now happy to accept any questions.